Hello, everyone, and welcome to today's exciting webinar. I'm Tim Stark, a professor of civil engineering at the University of Illinois at Urbana-Champaign. This is our first webinar of 2021, and most of the webinars for 2021 have already been scheduled with great speakers and timely topics, which are available on the FGI website. The next webinar is on the last slide today, and it will be on February 4th. During today's webinar, we welcome your questions and comments, which can be typed into the questions box in the control panel. You may send in your questions at any time during the presentation, and our speakers will address them at the end of today's presentation. The recording of this webinar, the related technical papers, and the PDF of the slides will be made available on the FGI website after today's presentation. A PDH certificate will be sent automatically to all who attend the entire webinar. Today's webinar speakers are Jim Collin, Augusto Lucarelli, and myself. Collin will start today and is the founder of the Collin Group and is also an expert in reinforced soil structures. I'll follow Jim, and then Augusto will wrap up the discussion with a presentation of his FLAC analyses of this case history. Augusto is a principal engineer with Itasca International in Minneapolis and has extensive experience with continuum deformation analyses using the software package FLAC. The title of today's webinar is Yeager Airport Reinforced Slope Failure Case History, Forensic Limit Equilibrium and FLAC Analyses. Jim and Augusto, thanks for squeezing this webinar into your busy schedules and joining us from Bethesda and Minneapolis. Jim, the webinar controls are yours.
Thank you, Tim. Next slide. Go. So this presentation today is a follow-up to the presentation that Ryan Berg and I did in August of 2020. Our previous presentation gave an overview of the failure and the forensic investigation. Today's presentation will provide a more detailed discussion of the 2D and 3D stability analysis and then the deformation analysis performed during our investigation. Next slide, Tim. Since our August presentation, we've had two journal articles published. The one on the right is from geotextiles and geomembranes, and it deals with the overall case history and the details of that, and really is the companion to our August presentation. The second publication, the one shown on the left, goes into great detail on our stability analysis and our deformation analysis, and it's really the companion document to our presentation today. Next slide, Tim. So my job today is really just to, it's easy, it's just to set the stage, give a little bit of background on what we've done, and then turn over the presentation to Tim and Augusto to talk in more detail about the stability analysis and deformation analysis. Next slide, Tim. So I'll set the stage, talk a little bit about the failure, and then turn it over. In August of 2005, the construction of the RSS started. December, it took over a year to complete the construction. It was completed in December of 2006. In 2010 through 2014, there were shallow superficial slides at the base of the RSS, which the base of the RSS was actually 100 feet above the road below the slope. In July of 2013, the first tension crack in the EMAS above the reinforced slope was noted. And then in 2015, in January, settlement was first observed. And then March 12th, 2015, total collapse occurred. Next slide, Tim. Here we can see the reinforced slope. It's 240 feet high. The green area on the right of the figure there is the 1-to-1 slope. The area where the shadow of the airplane is a 2-to-1 slope that was unreinforced. and it terminated at a flat location several 150 feet above the road below the slope. Next slide. Here we can see the failure that occurred on March 12th. Prior to the failure, there were residences located in the failure mass that were evacuated. There was no loss of life, but you can see in this slide that the road Keystone Drive below the runway was blocked and several structures were destroyed during the slide. Next slide, Tim. This is a little better close-up. You can see the slide debris has crossed the road. It's actually blocked a creek that's caused flooding upstream. The slide mass continued to deform with time, and that church shown in this picture was taken a couple weeks after the slide occurred. Next slide, Tim. In this slide, you can perhaps see how the reinforced slopes really just dropped down. That headscarp was over 100 feet in height. Next slide. So a little background. The original design was, as shown in this figure, the purple area is the reinforced fill. It was designed to sit on rock. 175-foot long reinforcement lengths. The bottom 17 meters of the reinforced slope reinforcement was spaced 1.5 feet apart, and for the rest it was 3 feet apart. The geology of the site, there was shale in the lower portion of the RSS, overlain by sandstone, and then in situ fill. Next slide. So that was the original design, but the design changed during construction, and there were significant changes that led to, I think, a lot of the problems that we've observed. First, instead of excavating out the 175 feet of rock as the original plan called for, the excavation went back to the rock face and terminated. So grid lengths now were 75 feet instead of 175 feet. And the surface of that rock is not stepped, but it's at an angle, which led to some of the issues. Below the bottom of the reinforced slope, they actually excavated another 10 feet, and that was replaced with material that was unreinforced. So those were some of the changes that we'll review as we go through the analysis to see how they impacted the stability of the slope. Next slide, Tim. So from our analysis, we concluded that the failure was compound, that it extended below the bottom of the reinforced mass, went back across that shale interface, and then up through the reinforcement. And it collapsed 8 years after being in service, and we found that the shale claystone interface strength had decreased from its peak strength to somewhere near its fully softened strength. Next slide, Tim. So I'll talk a little bit about the laboratory testing, and then Tim's going to take over there and then continue on. So next slide. The reinforcement that was used for the slope was a polyester geogrid, and it had the manufacturer submitted the reduction factors for creep, installation damage, and degradation. The specifications for the project were such that there were minimum creep reduction factors and installation damage factors. So you see in the first column here, the RFCR, the creep reduction factor for the materials, that's what the manufacturer had from their testing. What was required is in the next column, so they actually used a higher reduction factor for creep, and the same thing on installation damage. So the design was based on these allowable strengths of 35 and 4,500 pounds per linear foot. Next slide. So that 100+ foot headscarp had to be stabilized prior to any remediation work that could be done. During that removal of the headscarp, our forensic investigation started that included collection of samples of the geogrid at multiple layers during the deconstruction. We took those samples and did a random sampling pattern of those, and then went to a lab and tested those. So if we go to the next slide, we'll see some results of that. We did both wide width tensile tests and single rib tests on the exhumed samples of both the two grades of grid. You'll see that the wide width tests are slightly less than the single rib tests. And we find that it's difficult with these high strength materials to load them in a wide width test without some zipper effect. And then certainly if you have one damaged longitudinal member in that wide width test, that would fail first and cause the zipper. So we elected to use the single rib tests for our analysis, and we used 9,000 pounds per foot for G grid A and 10,000 for G grid B as the exhumed strength of the material. Next slide. We were able during the deconstruction to expose the slide surface. We exposed approximately 120 feet of it. You can see here it was readily available, the surface. Samples were taken by all the defendants, experts, to do analysis of the material. And with that, I'm going to really turn it over to Tim to talk about some of the testing that we did on that material.
Great. Thanks, Jim. So I want to start with the laboratory testing of the soils that Jim and his crew obtained from the failure surface. As Jim mentioned, the strengths that we were interested in were fully softened strength and residual strength. The structure had been in place for 8 years, so we knew peak was sort of an upper bound, which you'll see in a minute was used as 36 degrees in the stability analyses for the design. But over 8 years, thinking that there would be some softening, so we took the samples from the failure surface, reconstituted them, and made normally consolidated specimens to measure fully softened and residual strength. So we tested 3 samples. They're shown on these 2 slides. The liquid limits from 32 to 40, plasticity index 11 to 19, and a clay size fraction of 45 to 46. So that bumps it into the 3rd group of our correlations. And that yields a fully softened friction angle that's stress dependent from about 27 at low stresses to 21 at higher stresses, and 18 to 13 in terms of residual friction angles. You can see the stress dependent envelopes here, and those were used in the 2D and 3D stability analyses that I'll talk about in just a minute. Here's the last specimen that was tested, or sample that was tested, and similar plasticity, a little higher clay size fraction, fully softened of 26 to 20, and a residual in the same neighborhood of 17 to 14. These results are in good agreement with our fully softened and residual correlations. Really, that's the most important use of such correlations, is to verify the laboratory results, whether you're doing them or a commercial laboratory is doing them. Really make sure that the laboratory data makes sense, make sure that the fully softened strengths that are being reported are not at or below the residual strength envelope, which is green on this particular slide, and just make sure they make sense. Really the best use of the correlations. Okay, using that data in the stability analyses, Jim showed a cross section with the various zones, which are shown on the left, reinforced in situ, bearing soil at the toe, and then the soil rock interface that developed a softening, and you'll see a stress dependent envelope being used there. 36 degrees used in the original design. Okay, here's the 2D limit equilibrium results, and then I'll look at 3D. So there are 5 design cases or 5 analysis cases. So bear with me here so you understand the 5 which are used in the 3D analysis too. There's the initial design, and the RSS is based on rock or founded on rock, and it uses the long-term design strength of the grids that Jim mentioned that had the creep, the degradation, and the installation damage. So the grid strength was fairly low at 66.1 kilonewton per meter, which translates to 4,500 pounds per linear foot. The grids also had their full length of 175 feet and using 36 degrees for the soil materials involved. Second is the revised grid length, so dropping it from 175 down to 80. And then last case that I'll focus in on at the moment is the end of construction, where the exhumed geogrid strength, so what was tested from the field after the failure, so it does not include the creep or degradation. So it's a higher value, notice 145.9 versus 66, and 145 is the 10,000 pounds per linear foot that Jim showed you just a minute ago. So here are the factor of safeties for these first 3 cases, all with no water. So 1.5 for the initial design. If the grids are shortened from 175 to 80 at the bottom and 175 at the top, there's about a 7% reduction in factor of safety. And then the end of construction is 1.7 because this analysis only uses the installation damage. In other words, the grid strength is much higher than 1 and 2. But still, these factors of safety are at or above 1.5. So let's go to the second, or the 4th and 5th, or the last 2 analyses. End of construction with fully softened strengths now at the interface instead of the 36 degrees, and then failure where the grid strength will be reduced for the effect of creep due to the deformation that was occurring at the top. The tension crack that developed, the settlement that occurred, and that lowered the grid strength from 145.9 to 84.8. So that's the big difference between 4 and 5 and fully softened strength being used. So here, the 2D factors of safety go from about 1.15 down to below unity for a range of groundwater conditions, dry to high. These were estimated, dry, low, medium, high, to get a range of factor of safety as a function of water level. So the end of construction case is still about 1.5. There we go. Oops. And then as the creep affects the geogrids with the movement at the top, the strength of the grid is reduced for creep, and now the factor of safety ends up right about unity. And if you look at 0.99, call that 1, a medium groundwater condition, but clearly low groundwater condition, you're right at 1 as well. Okay, so that brings the 3D equilibrium analysis. The 3D equilibrium analysis was conducted to model the overlap, the anisotropy in the uniaxial geogrids, the different grids that were involved, and the variation of groundwater across the slope. So this is a plan view from the 3D analysis. The darker strips are the lower strength geogrid. The lighter strips here in the middle are the higher strength geogrids. So that's the difference in the grids. You can see the overlap of the grids here at the slope nose that was accommodated in the 3D analysis, as well as the anisotropy of the uniaxial grids, which I'll come back to in just a minute. So a 3D analysis in general yields a higher factor of safety than a 2D analysis, because if you look at this levee along the Illinois River here, if that's infinite in both directions, if you take a 2D cross section right through here, the end effects of that infinitely long levee are small compared to the overall shear resistance generated along the length of the levee for a failure surface going from, say, the crest of the levee into the river that's over here on the right. Of course, slopes are not infinitely wide, so these end effects can significantly influence stability. And so I want to review that very quickly before we get into the Yeager case. So if you have a dam such as here with a curved axis, if you cut a cross section down the middle of this dam, you'll be underestimating the factor of safety because of the 3D effect by this curved shape. Same with this photograph, a New Maloney's dam. It's a curved shape. If I take a 2D section down the valley, I'm not incorporating the 3D effect. So in general, a 3D analysis should yield a higher factor of safety. And that's shown in this graph that we developed for the comparison of a 3D to a 2D factor of safety. So notice for a 5-to-1 slope, it could be as high as a factor of 2. For a 1-to-1 slope, which is what we're talking about at Yeager, it could be as high as 30%, depending on the width of the slope and the height of the slope. So Yeager is a 1-to-1, so a maximum of, say, 30% increase due to the 3D effect. Okay, so just to make sure everybody followed that, I have a quick quiz for you that you can type the answer in the chat box. The question is, this is a landfill. A design cross-section is cut right here. And the quiz is this the critical cross-section for the 2D analysis? These are the contours up from the ground surface to the top deck of the landfill, which is up here. We'll answer that in the questions. Okay, so let's turn to Yeager. The failure direction is shown by the red arrow, and so our grids will be compared to this failure angle, and this is also the angle or orientation of the 2D analysis. This is what a uniaxial geogrid looks like. It's strong in one direction, say in that the machine direction where it's elongated, and it is much weaker in the cross machine direction if you pull it this way. And the testing that was conducted for Yeager, there's a 90% reduction between the machine direction to the right and the cross machine direction upward. And we include that in the analysis, which I'll show you in just a minute. So Jim showed these test results earlier. The new column to the table is over here on the right, which is the cross machine testing of the geogrid. So notice the geogrid has lost 90% at a orientation of 60 degrees from the machine direction. So if you pull on that grid 60 degrees from the machine direction, you're at 90%. And of course, if you go 90 degrees from the machine direction, you're at 90% reduction as well. Same with the stronger grid. You can see the cross machine is only about 1,000. Again, 90% reduction. So we include that in the 3D analysis, which I'm going to describe on this slide. So each layer had a construction drawing, as you see here in the upper left. The length of the grid, the rectangle representing the grid, and then as it came around the nose, how the grids overlapped each other. So there are 85 layers of geogrid that we inputted into the 3D analysis. 85 different layers, digitized each one of these drawings 85 times to build up the slope. This particular drawing's at elevation 875. We used method A in the stability analysis to represent the reinforcing force. So how did we incorporate the 90% reduction in the strength? Here is the orientation of the failure by the first red line. Then we took the orientation of the grid, say this particular grid right here. This angle, we checked this angle on each level and each grid from the failure direction. And any angle that was greater than 60 degrees, we applied a cross machine strength or a 90% reduction. Here's a close-up of the scarp that Jim mentioned, and this gives you a great view of the close spacing of the grids. In the lower portion, the grids are spaced every 1.5 feet vertically, and in the upper portion, which is shown here, every 3 feet vertical. So all that are shown here are the ruptured grids on a 3-foot spacing. There's a picture of the grids being installed during construction. You can see the overlap right here that we modeled in the 3D analysis. Okay, so here's a typical result from the 3D slope stability analyses. This happens to be for the high groundwater condition, the failure condition, fully softened strength on the soil rock interface, and notice the factor of safety is 0.95. The medium groundwater condition gave about 0.99, as you saw on a prior slide. So let's look at the comparison of the 2D and 3D factors of safety. First, the 3D factors of safety, 1.65 is if the grids are isotropic, so there's no change in strength with direction, and with anisotropic behavior of the grid included, you can see it drops the factor of safety about 8%. And that was kind of typical. All cases between 5 and 15% drop if you include the anisotropy of the grids. If the grids are not anisotropic, if they're truly isotropic, then there wouldn't be a difference. But we did include the anisotropy of the grids, as I mentioned, using the angle of 60 degrees. Now let's compare that to the 2D factor of safety. So if I use isotropic strengths in the 3D factor of safety, the 2D factor of safety is about 8% lower. So remember on our 3D comparison chart of factor of safety for a 1-to-1 slope, that should be up around 10 to 30%, but you can see it's only 8%. So with an anisotropic situation, you're not getting the full benefit of a 3D analysis. In other words, all that conservatism that's built in, or you think is built in because of three-dimensional geometry, is not being included. You'll see that in just a minute again. So here are the last two cases, end of construction and failure with isotropic and anisotropic grids. So fully softened strengths, you can see with the groundwater going from dry to high, 1.4 to 1.27. And then with anisotropic, you go from 1.27 to about 1.1. So almost at failure. And then at failure, including the reduction in the grid strength to account for the creep in the upper portion. You can see even with isotropic behavior, medium to high groundwater about 1.0, and with anisotropic grid behavior, only need a medium groundwater level to be right about 1. I showed you the slide mass, 3D slide mass for this case of 0.95 a couple slides ago. Okay, so failure without isotropic grids and high groundwater, or failure with anisotropic grids and a medium groundwater condition. Okay, so let's take a quick comparison of 2D versus 3D factors of safety. So in the 2D analysis, the grids were modeled with an isotropic tensile force because you're only looking at one direction. In the 3D analysis, we can include the anisotropic behavior because we can vary the orientation of the grid. So for the original design, there's only a small difference between 2D and 3D. In fact, the 2D is approximately 3D instead of 10 to 30% higher for a 1-to-1 slope. So that's important. You don't have that extra conservatism built in when the grids are anisotropic. Yep, so the 3D is not 10 to 30% higher. And lastly, the 2D is not conservative with uniaxial geogrids. In geotechnical engineering, we do a lot of two-dimensional slope stability analyses because we think we have some extra conservatism built into the analysis because we're not including the end effects. But here with an anisotropic grid, you're basically don't have an extra reserve of end resistance that's making your slope even more stable. So the 2D is not conservative. It's about the same as the 3D analysis, which I think is a very important result from this particular case. So let me wrap up and then turn it over to Augusto. Not accounting for anisotropic tensile resistance decreases the factor of safety, the 3D factor of safety, 5 to 15%. 2D stabilities are not conservative with anisotropic reinforcement, like we see generally in soil mechanics or soil slopes. Failure occurred with anisotropic grids and a medium groundwater condition because uniaxial grids were used. The 3D factor of safety that should have been used for design has to be greater than 1.5. If you want to match the same level of safety as a 2D factor of safety, because again, there's some extra side resistance, you'd have to use a 3D factor of safety of 1.9. And I'll include a paper with the video and PDF that'll explain why the 3D factor of safety has to be higher than 1.5 if you're going to get to the same level of safety as a two-dimensional slope stability analysis. Okay, it's great for us to have Augusto Lucarelli with us to talk about his continuum deformation analysis.
Thank you, Tim. Okay, good morning, everyone. We are just going to go through a brief overview of what has been the numerical FLAC 3D analysis. I've used FLAC 3D, but essentially it is a 2D cross-sectional analysis building the cross-section TT that we have seen so far that has also been used for the 2D limit equilibrium analysis, just extruding in the autoplane direction for a certain thickness. The thickness of the model has been considered 0.25 meter. There is no particular reason for deciding that number other than being able to generate a grid dimension that is consistent with the spacing of the grid and being able to capture the interaction with the geogrid. On the upper corner, we see the size of the model, the shape of the cross-section with different colors of group. And those are representing the construction stages. So during the modeling processing, also the construction stages was accommodated in the model, starting from the original shape of the slope, and then the excavation, and then building up in layers and activating the geogrid at the same time. The full RSS. The purpose of that is to try to establish a realistic initial stress distribution inside the reinforced slope, and also to try to have an idea about what could have been an initial mobilization of stress, strength, and strain inside the geogrid. In the lower part, the bigger zoom represents the interfaces. In particular, we have two types of interface. The clay shale layer, which is modeled with zones, and then the RSS rock interface, which is a simple interface. The gray is the RSS, and the yellow is the bedrock. Next slide. Okay, this is just a detail for those of you who are interested in the mesh and modeling. I try to keep, again, a mesh size that is compatible with the spacing of the reinforcement, and also try to have a model that runs relatively quickly because of the numerous different cases and scenarios that we plan to run. And 0.25, 0.25, and 0.25 also in in the outside direction. Just to give you an idea, the model has about 75,000 quad dominant zone and 150,000 grid points. And one run would take, it was in the order, it depends on the computer as well, but just to give you a broad perspective, it's in the order of a few hours, 2-3 hours to run a full model. Next slide. Okay, one of the extra parameter that we have to give and we have to consider when we are doing a deformation analysis with respect to limit equilibrium is that we need to give some stiffness to the material that we are modeling. In particular, two cases have been considered just to see what could have been the effect of different stiffness distribution inside the soil mass, and also stiffness and strength distribution of the interface between the reinforcement and the soil. In particular, case one has a constant stiffness of 60 megapascal for the full reinforcement, for the full reinforced soil, and the case two has a function stiffness that is dependent on the strength, on the stress inside the soil mass. Obviously, this seems to be a little bit more realistic than this one. In this particular case, I can just tell you since that there isn't a significant difference because the failure essentially occurs outside of the reinforced soil. There is a slide that is here and marginally involves the bulk of the geogrid. Only in this area are involved. But what we have seen as a difference is the mechanism inside, the evolving mechanism and mobilization of strength and strain of the geogrid inside the soil mass that was a little bit different. Next slide. Okay, modeling the geogrid. For modeling for the geogrid, let's say the thickness of the model was 0.25 meter. So I've decided to lump all the geogrid that are in 0.25 meter inside one single cable. You see the red dot on the upper right corner, that represents our reinforcement. And so whatever was the strength and stiffness inside the 0.25 thickness of the model was lumped inside that single element. A cable element is essentially a uniaxial structural element that only carries axial force. It can yield, and we need an element that can yield, and not only yield, but it can also rupture. Once the strain reaches the final ultimate strain, the cable element is deleted from the model, so that we are able to see the progression of the failure mechanism while the mass slide downward. Next slide. Okay, this represents the stress and strain mobilized at the end of construction using the geogrid as exhumed properties. We see that from the upper left corner that the strength is in the axial force is in the order of 5.7 kilonewton in comparison to the 35 limit, so relatively low in terms of axial force mobilized inside the geogrid. And also, if we look at the strain on the lower side, we are on the green area in the order of 1% mobilized strain inside the reinforcement. If we have keep in mind that usually, let's say, a failure rupture strain is in the order of ballpark 8–10%, those numbers seems to be relatively safe. There are marginal mobilization that are going a little bit higher, but are very localized and probably not so significant. Next slide. Now, this shows the effect of inducing some pore water pressure at the interface here at the bottom of the mass. Of course, once we have the possibility to generate pore water pressure inside, we are reducing the effective stress in the interface, and therefore we are in less strength available, and we see the mobilization of some displacement, which could be in the order of, let's say, in this case, we are getting 0.26 meter. roughly 6-8 inches. And we also see a different mobilization effort inside the geogrid here in the lower part. Not much different in terms of maximum value, but much more extended in terms of within the length of the reinforcement. So if you remember the slide before, the green was only in this first part, but now the greens and the yellow tend to extend all the way back to the end of the reinforcement length. Next slide. So what happened once we start mobilizing, either for, let's say, poor water pressure, or also because we are inducing a level of shear stress inside that clay shale layer that would trigger more creep inside that material as well, that probably has not been exposed before. For whatever reason, we start mobilizing some displacement inside the soil mass. We have we see that potential tension crack may appear at the top, and that actually was observed at this location at the top of the slope, the formation of a tension crack where the model is predicting it. And also the other aspect is we have a significant now volume of the reinforced soil slope that has reached the 2% strain mobilization. Okay, next slide. Now, all this part, the initial part, is necessary because once we want to do a strength reduction analysis, we have to have a model that is in equilibrium, and then we are starting to reduce the strength of a certain component or a certain volume until we determine what is the failure mechanism and the strength of the whole system. In this particular case, we know that the failure happened at the bottom, and so the idea was to reduce the strength of the interface of clay shale layer, starting from an initial assumed strength, which was the red dashed line, and this is also a power law expressed with a A08 and a B09, so almost linear, which is consistent with those 36 degrees that we have assumed. And here overlap, you have the lab tests that are showing in these fat lines where the fully softened strength is falling. So the idea is to start from this configuration, which is the top, the dashed line, red, and then gradually slowly reduce the strength of that material until we detect some kind of failure. In particular, keep in mind these two numbers, A04, 044, which are the A parameter for the lab test. Okay, next slide. During the process, the strength reduction, obviously there are different quantities that are monitored. First of all, we need to decide when failure is occurring and what is the type of what is the measure that we are using to detect failure. In this particular case, you see these red lines and these black lines. Without getting into the detail, you see that up to a certain extent, the red line is flat, and then at a certain point, you see a breakout. The same thing for the red line is a little bit more wiggly, but at some point it's like a sort of a financial trend analysis. You break up the top and the model becomes unstable here. And you see here at the top on the upper left, the rupture of the geogrid exactly where have been observed on the side. It is also interesting to see how the model can somehow show the internal mobilization of strength. You see many shear bands inside the RSS, and those blue points are showing where the geogrid might have broken because the element has been completely deleted. We have a video later that is showing the progression. Now, on the lower corner, we see the mobilization of the displacement during the strength reduction process. In particular, the red line and the blue line are showing the maximum and the average displacement for the RSS. First of all, we see that there isn't a significant difference between the average and the maximum. That tells that essentially everything is kind of moving down pretty much like a rigid body, and that is consistent with the fact that we have essentially a failure of the foundation mostly. What we can also see is that there is a region in which we have a acceleration of displacement, and this is the value for which we have the formation of the crack at the top, and then once we are approaching this 1.5, we have the mobilization of the fault failure. So the A minimum, the strength reduction has been carried out reducing the A parameter with this factor RSS strength reduction is the failure happened for 1.46, which correspond to an A minimum of 0.53. This was for a medium configuration of water pressure. Next slide. Now, this chart puts everything together. We are not going to go into much detail for other cases, but essentially that was showing one case, and we have the summary is, okay, starting point is the dashed red line. The blue lower curve are the fully softened, and the line in between are showing the failure envelope corresponding to different level of poor water pressure. So no medium intermediate, intermediate will be medium and maximum. And these are the A parameter that are corresponding for to the failure. One aspect that we see is that with a 2D analysis, we are not able to even go all the way down to fully soften. And if we compare the ratio, take the fully softened strength that was measured in the lab multiplied by 1.3, we get a 0.55, which is close enough to what we have in terms of A for the medium water pressure. And that's kind of a latch into what Tim was saying between the 2D and 3D safety, factor of safety comparison. The case for 2A and 2D are essentially the comparison, the effect of the stiffness distribution inside the RSS. Remember that I said that there are two cases, one is constant and one is stress dependent. You see that in this case, there isn't a significant difference. In particular, for the dry, we get 0.5 and 0.5. And for the maximum water table, again, we get the same number. So the stiffness distribution inside the RSS in this particular case is not significant, but there are other cases or situations where it could be important. Next slide, I think I'm pretty much done. Oh, no, then we have the video, okay? So this is showing the progression of the strength reduction, and Tim is accelerating now. You see in green, the axial force is mobilized, and you see the two lines that are detecting the displacement of the RSS, and you see these shear bands forming inside while the mass is sliding all the way down. And all these are essentially situations in which that have determined the failure of the geograde inside the soil mass. Obviously, this is a continuum analysis. We cannot capture the full failure all the way down. We would need to adopt a completely different type of approach, but it's still, let's say, informative in terms of being able to capture what happened on site, and in particular the location of the emergence at the top here of the failure is in between 2-3 meters from what have been observed on site. Next slide. Okay, I'm done.
Thanks, Augusto. The forensic analysis performed by our 2D, 3D limit equilibrium and our 2D deformation analysis were all consistent. And they were also consistent with our observations during the forensic investigation and deconstruction of the slope, leading us to the causes of the stability problems were, one, shortening of the geogrids on the slope, not bearing the slope on rock, but on a weathered material that lost strength, and reduction in the tensile strength of the reinforcement once we got large deformations to exceed the creep limited strength, and the impact of water. And why the impact of water was not significant in changing the factor of safety. We do believe that the water was significant in the deterioration of the strength of the material from its peak strength to its fully softened strength. So with that, I'll turn it over to Tim. I think he has some closing remarks. And if we have times for some question and answers, I believe.
Yep, let's do some questions first, Jim. There's a bunch of questions. Let me start with the ones that are focused towards you, and because you're on right now. Why were reduction factors greater than 1 used? Isn't that overly conservative?
I'm not sure I understand. The reduction factors for the reinforcement are factors to account for forms of degradation, and so they would all be greater than 1. These were pretty well established reduction factors based on the National Transportation Product Evaluation Program.
Okay.
I'm not sure if I answered that. I'm not sure if I understand the question correctly, Tim.
No, right. They have to be greater than 1, otherwise you're really not reducing the strength, and that's the whole point, is to reduce the laboratory tensile strength for field applications. Jim,
right.
What were PE grids, polyethylene grids, considered for the design? If not, why not instead of the polyester?
So we were not part of the original design team, but the original design team, I think, originally designed based on polyethylene grids, and the supplier submitted for polyester grids, and those were evaluated and accepted in the end.
Okay. Next is the 1-to-1 slope the steepest possible? Could it have been a steeper slope, assuming they were putting it on rock? Was there any limit to 1-to-1?
No, and in fact, in other parts of the world, we're doing reinforced slopes that are significantly steeper than 1-to-1. So there's not a limit on the ability to create a steepened slope steeper than 1-to-1.
Okay. What elevations were the low, medium, high groundwater levels, and were there any field observations, confirmations of the groundwater levels?
So it's a 2D, so it's not any specific elevation for the groundwater. I'll refer to our papers that'll show where the groundwater was modeled. We had no instrumentation of this structure prior to failure, so it was a 240-foot high structure, the first in the U.S., yet there was no inclinometers that had been installed. There were no strain gauges, no pore water pressure monitoring. There was no monitoring other than surveying that was done as part of the original design.
Okay, I'm going to knock off a couple easy ones here. What was the water acting on the clay shale interface at the trigger of the slide? So based on limit equilibrium, it looks like around the medium level, low to medium level. How well did the 3D analysis failure surface / slide mass match actual failure surface? I thought it was really amazingly close. So good representation of the 3D slide mass in the limit equilibrium analysis. And of course, we tied the points at the top, the bottom, and the sides to sort of help the model generate a representative 3D slide mass. Okay, next. These are kind of coming in quick. Augusto, this is a question for you. What were the evaluations 2D, 3D, and FLAC 3D concurrent? Was the FLAC 3D performed independently without prior knowledge of the 2D or 3D factors of safety / limit equilibrium? When were the results between the two methods compared? How were the different evaluations presented? FLAC to compare the 2D and 3D, or the 2D, 3D to confirm the FLAC? Or Jim, both of you guys can answer this.
Gosh, this is quite a long, and I'm not sure I remember exactly the whole procedure here. But if I recall correctly, I tried to keep these as independent as possible with the minimum interaction, at least at the beginning, to try to see what we were getting to, by using two different methodology and how far are they? Are we close enough? What would be the difference, and so on and so forth. In the end, it turns out that, yeah, there are some differences, like the pool water pressure, for example, in a continuum analysis seems to have an impact. In a limit equilibrium analysis seems to have a less impact. But the results were pretty close, and what I was comparing mostly, we were comparing with the 2D limit equilibrium analysis. We didn't have the chance at the time to set up a full FLAC 3D analysis. We ran out of time for that.
And I would only add to that the 3D limited equilibrium analysis was done after we did both 2D analyses.
Yeah, correct.
Okay, I'm just going to keep going. There are many questions. We're not going to get through all of them. Can you comment on whether you observed geogrid rupture in the field that appeared to be a transverse grid failure and not a longitudinal grid failure? Such observations would provide support for your anisotropic grid strength characterization. Jim, maybe that's you.
So we didn't have time to go into how we deconstructed the slope, but in the failed mass, the grids were really a jumbled mess, and there was no way, I think, to really determine how they failed within the mass. So we couldn't do that. When we deconstructed, the grids were intact, so they hadn't failed. So in essence, no, we were unable to observe ruptures that were orthogonal to the direction.
Okay. I'm just going to keep going. Could this model be used for cyclic loading, seismic loading? If so, what would the reduction factor be to determine a post-earthquake strength, for example?
What model?
Well, let's do limit equilibrium, Jim. Why don't you handle the grid? And in limit equilibrium, of course, we could simulate that with a pseudostatic force. But why don't you talk about the grid first?
Well, in a seismic event, the grid strength would be higher, right, than its long-term strength. So yes, but we modeled at failure. So there we used the creep limited strength. If we were modeling just a reinforced slope for a seismic event, we wouldn't use the creep limited strength. We would use less of a reduction to account for that short-term loading.
Yeah, and as far as the FLAC 3D analysis, of course, I would have set up the model in a different way. That shape is not compatible with a dynamic analysis, but yes, it's possible to model, and it has been done, and there is no particular issue.
Okay. Does the 90% reduction in geogrid tensile strength at the 60-degree skew refer to the ultimate or at 5% strain?
Ultimate strength.
Great. How are the strengths and directions neither perpendicular nor parallel to the machine direction determined? Were these available in tables from the geogrid manufacturer, or was project-specific laboratory testing needed to find these values? And Jim, I'll let you do that. Go ahead.
Yeah, we did project-specific testing on the grid to determine that.
Right, and with the air angle was varied in the test. We didn't present any of those results. We just, right? They varied.
Right. We did it at 90, 75, 60, 45,
right,
30, I believe.
Geez. Did the creep reduction factor and the overall reduction factor considered, was it on the low side of those typically used for uni-axial geogrids?
Well, the low side, the creep reduction factor was the as tested creep reduction factor for that product, right, at the time. So I think it was, I don't remember exactly, I think it was like 1.6. I think the low end for polyester creep production factors now is in the 1.5 or 1.45, somewhere as low as that. So it wasn't in the lowest range of the creep production factors for polyester.
Okay, we're not going to get through all of these. We will have a follow-up podcast where we'll address the remaining questions. I'll do one more, it's pretty quick. Does fully softened strength condition represent the parameters equivalent to undrained condition parameters? No, the fully softened strength is a drain strength, and it's basically a drain strength that corresponds to a normally consolidated specimen. So the effects of compaction, for example, or over consolidation have been removed. So we will record a follow-up podcast with all of these other questions. So let me wrap up here. We're right at the top of the hour. Okay, here's contact information for our speakers, Jim and Augusto. If you have additional questions or want to contact them, please do. You will receive a post-webinar survey where you can submit additional questions that we will answer in the podcast, upcoming podcast. Our next webinar is geomembrane attachment and penetration design and installation. That is Thursday, February 4th at 11 a.m. Central Time. Pat Elliott of Raven Industries and Duff and Brendan Simbeck of Simbeck and Associates will be the presenters. Please visit our website for the online PDH program where you can watch prior webinars and receive a PDH letter for 1 hour for each webinar. Thank you everyone for attending. Jim and Augusto, thank you so much for doing a follow-up on the Yeager airport failure and discussing the specifics of our analyses. And I look forward to our upcoming podcast. Thank you everybody for attending.